Our planet is anything but flat, right? It's covered in these incredible mountains, deep valleys, and just massive, sprawling plains. But why? Why isn't it just a smooth ball? Well, today we're going to dive into the story that's literally written all over the Earth's surface to figure out just how it got its shape. Yeah, it's one of those simple questions that's actually really deep. Why isn't our planet a perfectly smooth sphere? I mean, what kind of colossal forces have been at work for billions of years, sculpting and cracking and pushing up the surface to create the world we see today? That's the exact mystery we're going to get into. So, the answer to why the Earth looks the way it does, well, it all comes down to one powerful idea that basically covers every single bump, every valley, and every peak out there. And that word is relief. It's basically the scientific term for the grand total of all the ups and downs on the planet's surface. And I mean everything. Just think about it. From a tiny little riverbank all the way up to an entire continent, this one word covers every single landform, and each one has its own unique story of how and when it was born. Okay, so to really get a handle on this whole relief thing, we've got to look at it at every scale imaginable. We're going to start way out in space with the whole planet in view, and then we're going to zoom all the way in, right down to the kind of details you might notice on a weekend hike. All right, first up, mega relief. This is the biggest picture you can possibly imagine. We're talking about the most fundamental split there is, the continents, where we all live, versus the massive, deep ocean basins. These aren't just features on the Earth, they're the foundational blocks of the Earth's crust, forged way back when the planet itself was forming. And just to give you a sense of the sheer scale we're talking about here, the total difference in height on our planet, from the very tip of Mount Everest all the way down to the bottom of the Mariana Trench, is almost 20,000 meters. That's incredible. That's the massive vertical range of this mega relief. Okay, let's zoom in a little. Now we're at macro relief. These are the defining features within those continents and ocean floors. We're talking about things like entire mountain ranges or those huge, sprawling plains that just seem to go on and on forever. And if we zoom in even more, we get to mesorelief. Now, things are starting to look really familiar, right? These are the individual parts that make up those bigger structures. You know, the river valleys cutting through a plain, or the specific ridges and peaks that form a mountain range. And our final stop is microrelief. Now we're talking about the really small-scale stuff, where the change in height might only be a few meters. Think about the gullies carved out by heavy rain, or the bank of a little creek. It even includes things like the furrows left in a field by a plow. In fact, these features can be so small that human activity gets its own little subcategory, nanorelief. Pretty cool, huh? So this chart here really pulls it all together nicely. On the left, you've got the four scales we just walked through, from mega down to micro. And on the right, you see the scientific names for the processes that form them. You can kind of see a pattern, right? Geotexture is like the planet's fundamental blueprint. Morphostructure is the construction of the big stuff. And morphosculpture, that's all about carving the fine details. So what's actually driving all this building and carving? Well, it all boils down to this constant planet-wide tug-of-war between two opposing sets of forces. One set is always building the world up, and the other is relentlessly trying to tear it all back down. On one side, you've got the internal forces. Think of these as the Earth's architects. This is the raw heat and power from deep inside the planet that pushes tectonic plates around, smashing them together to build up enormous mountains. And then, on the other side, you have the external forces. These are the detailers, the patient, relentless work of wind, water, and ice that spend millions of years grinding those very same mountains back down to dust. And you know, there's no better place to see this epic battle play out than in the creation of mountains. They really are the greatest monuments to the raw power our planet can unleash.
Yeah, the scientific term for this whole process is orogenesis. It comes from Greek and it literally just means mountain birth or mountain creation. And it's all driven by the movement of tectonic plates, that incredible pushing, pulling, and scraping that forces solid rock to buckle and reach for the sky.
Now, geologists usually classify mountains into four main types. You've got fold, fault block, volcanic, and dome mountains. But for now, we're going to focus on the two big ones, the ones created by the incredible stress of those tectonic plates I was just talking about. So let's put two types head-to-head, fold mountains versus fault block mountains. One kind is formed when the Earth's crust gets squeezed together, and the other is formed when it gets stretched apart until it literally cracks. Here's a great way to think about it. For folds mountains, think compression. Imagine you've got a big rug on the floor and you push the ends toward each other. The wrinkles that pop up, that's basically a fold mountain. Now, for fault block mountains, think tension. Imagine pulling on a giant slab of concrete until it cracks, and huge chunks of it either get pushed up or drop down along those cracks. And believe it or not, every one of those wrinkles in a fold mountain has a name. The upward folds, the ones that create the peaks, are called anticlines, and the downward folds, the ones that form the valleys, are called synclines. The biggest mountain ranges on Earth, like the incredible Himalayas, were created by exactly this kind of massive squeezing force. And those broken pieces in fault block mountains, yep, they have names too. A block of land that gets lifted up between two faults is called a horst, and a block that drops down is called a graben. And maybe the most amazing example of a graben on the entire planet is the huge Great Rift Valley in East Africa. But of course, out in the real world, things are rarely this neat and tidy. The big takeaway here is that most mountains are actually a complex mix of all these things. They might show signs of folding and faulting and millions of years of erosion all jumbled together. That's why no two mountains are ever exactly the same. And all of this leads to a really mind-blowing thought. This whole process is still happening. Right now, as we speak, continents are shifting, new mountains are being pushed up, and erosion is constantly sculpting them. The world you see outside your window isn't the final version. It's a work in progress. Which really makes you wonder, doesn't it? What incredible new landscapes are these timeless, powerful forces creating for the future?